Well, a very happy Wednesday evening to everyone who's joining us, whether it be in our live Zoom classroom. We have at the moment 11 participants. There's usually a few that come in a little later. And we've got about the same number watching on YouTube, so thank you very much. This is a beginning class for amateur radio. Ham radio. Yes, it's still a thing, and I consider it to be the best hobby in the world. And I say that because with ham radio, your radio signal that you might be transmitting doesn't know about a border. It can cross borders and go around the world, and we do that routinely as amateur radio operators make contacts with hams in other countries. And so it's a lot of fun, and if you're intrigued, well, stick around and we'll get you going. My name's Gary. Ham radio call sign W4EEY, or in phonetics, Whiskey 4 Echo Echo Yankee. And we use this book from the American Radio Relay League. I always like to show the book. Right side up helps. This is the license manual for the technician. The technician is the beginning license level in the United States. This is the 5th edition book for this, and this is the book that you want. And in the back of the book, it's got all of the questions and all of the answers. Questions and answers to what? You get your ham radio license by passing a 35-question multiple choice test that you can take in your area at a local ham club or online. There's online testing as well, and then you can get your license from the FCC and get your call sign. And you can then begin to make radio contacts within the provisions of your license. So, in the United States, we have what we call incentive licensing. So as you get a higher level of license, you get more frequencies to operate on, and so on. So anyway, let's go ahead and get started. For those of you who haven't been in school for quite a while, or those of you who don't have any science or electronics background or whatnot, well, it's kind of like jumping off a cliff. Yeah, it feels like it's overwhelming, but don't let it get to you. As I've said, confusion is normal in getting started in this. Now, if you've got some electronics background, well, you've got a leg up on others, so maybe we can help each other out here. I did mention in our introduction last week that there are other personal radio services available in the United States. The Family Radio Service, the General Mobile Radio Service, Citizens Band. All of those may or may not require a license, but they don't require any testing. All you need to do is fill out an application and send your money, and the FCC will issue you a license. Well, I get asked, and we're going to talk about radio and signals fundamentals tonight. Why do I need to know that? Because all I want to do is talk on the radio. Well, in amateur radio, also known as ham radio, we have multiple frequency bands that are available to us, lots of different modes of operation, power levels up to 1,500 watts, and the ability to build and use your own equipment on the air. And because of this, and this is a worldwide thing. Amateur radio operators around the world have a similar challenge that they face, have to test with their local posts and telecommunications authorities to get their ham license because of these things. We want to make sure that we don't create interference to navigation or other issues, so we want you to have the basics of knowledge. And when you get your license, you won't know everything. You'll just have what we say is a license to learn. And we have a limited time frame. We'll be here for a maximum of 2 hours tonight, although I don't think we'll be here the full time. And we can't cover extensive electronics. So we're going to laser focus on the questions and answers, the test questions, and what the right answer is and why it is that. So hang on, here we go. This is section 2.1, radio signals and waves. And in all of our classes for technician, general, and amateur extra, blue text on a slide has significance. That means it probably relates directly to a test question. So it's something to pay attention to. And tomorrow, if you're on our mailing list, you'll receive an email from me with a link to a Dropbox folder. It's also in the description box of this video on YouTube. You can go there and get the handouts tomorrow. including a PDF of this presentation. So if you see links in this presentation or whatnot, you'll be able to get them tomorrow in the PDF. Numbers. We're going back to school. And we started last week, we talked about numbers and integers, and we're going to be dealing with whole numbers and fractions, decimal numbering, shifting units by thousands. I want to make you aware of scientific notation and the powers of 10, and then engineering notation, which is a subset of that, and plugging it all into the metric system and the metric system prefixes. America, in my lifetime, tried to move over to the metric system, and it was an utter failure. We stayed with the English measurement system, but science uses the metric system, and we're part of physics and radio. So the metric system prefixes that you see here, let me start up my laser pointer. So as I mentioned last week, for numbers greater than 1, these are the metric prefixes that we have to pay attention to. Kilo, for example, the symbol small k, it means 1,000. And in engineering notation, this would be expressed as 1 times 10 to the third. 10 times 10 is 100, times 10 is 1,000. So that's what all of these are equivalent. Mega is 1 million. The abbreviation is capital M. It's 1 with 6 zeros after it, 1 million, and 10 to the 6th power. 1 times 10 to the 6th would be the engineering notation. And giga, that's a billion. Right over here, 9 zeros. It's a G is the symbol, and 10 to the 9th. Now all of these others do exist, all of these prefixes, but the other ones that we need to be aware of are the ones then smaller than a whole unit. A milli, small m, that's 1/1000th of a unit, and that can be expressed as 1 times 10 to the minus third. Micro, that's 1/1,000,000th. You use the mu symbol here. Here it is in decimal notation, and here it is 1 times 10 to the minus 6th. And nano, 1/1,000,000th, small n. Here we are in the decimal notation, 10 to the minus 9th. And finally, the pico or pico, the small p. Here it is in decimal notation, 1 times 10 to the minus 12th. Now here, in our class, we won't be actually using the engineering notation in formulas or anything, but I want to make you aware of that because as we go to the general and extra class, you will. Now the metric system has a lot of benefits. It's repeatable. It's based on the number 10. You multiply or divide by 10. It's called the International System of Units. It's used across all sciences, whether it be those in biology and microscopy, looking at very small things, or whether it be in astronomy, looking at great vast distances. It's easier to use this system because it's convertible and works well in formulas and in understanding things. In the English system of units, pounds, ounces, feet, miles, it's not so readily convertible. So that's why we stick with the metric system. Now, you're already using powers of 10 every day. You may not realize it. Think about, well, maybe it's not in your wallet anymore, but think about cash and the money that we use. Well, let me give you a little memory jog here. Let me take you on a trip to a place that I call Garyland. All right, it's an imaginary place. But in Garyland, the money that they use there is the Gary buck. Whoo! There's 1 Gary buck. That's the base unit. And if we were going to use metric prefixes, well, we might have a bill that is worth 1,000 Gary bucks, or something worth 1,000,000 Gary bucks, or something worth 1 billion Gary bucks. So again, the 1, that's the base unit. But take a look here. Here's 1 kilo buck. So the metric prefix kilo for 1,000. And here we have it, a kilobuck. Here's a megabuck. Don't take this to the store and try to, cash it. They'll probably look at you funny, but that's a megabuck. And then a gigabuck. I'd like to have that in my wallet and have it be worth something, but no such luck. And then for the numbers below 1, Bruce, you can take me off. There we go. So milli is 1/1000th. Micro is 1/1,000,000th. Nano is 1/1,000,000,000th. And pico is 1/1,000,000,000,000th. Well, we can have coins. We can have a millibuck, or we can have a microbuck, or we can have a nanobuck, or a pico or a pico buck, whatever you want there. So here's a link to a YouTube video that talks about conversions from one unit to another. We're going to do some practice problems here in just a little bit, and I think you'll get the hang of it. For a lot of people, though, this is headache inducing, and so I just want to assure you, you will get it. So practice problems are coming up, but for the moment, let's make waves. We're going to make RF waves, and when I say RF, that's an abbreviation that means radio frequency energy of any kind. So if somebody says, I'm getting RF interference, that means that you're getting interference from radio frequencies coming in to whatever you're talking about. And radio waves are analogous to the ripples on a pond. If you drop a pebble in a very still pond, you see the waves that come out from that central point. Well, think of that central point as your antenna, and the waves, the radio waves, radiate out from that antenna. And we like to use graphs, and so in the time domain, with time on the horizontal axis and amplitude on the vertical axis, this is a representation of an electronic sine wave generated electronically. It's got 0 volts here. It goes up to a positive amplitude, a positive peak, comes back down to 0, goes to a negative peak, comes back to 0, and alternates. This is alternating current, or AC. And at 60 hertz, it's the AC that comes out of the outlet on the wall there that powers your computer, etc. But at very higher frequencies, and by that we mean it happens more often per second, for example. So low frequencies, medium frequencies, see the alterations are happening more often, and then high frequencies. So frequency is defined as the number of complete cycles that occur in 1 second. So for the power outlet on the wall, 60 cycles, or 60 hertz, that happens 60 times in a second. For radio waves, it might happen 1,000,000 times in 1 second. So you can see there's a range there. And then the definition of period is the number of seconds or microseconds or milliseconds or whatever it takes to complete 1 complete cycle. So frequency is the number of complete cycles in 1 second, and period is how long it takes to complete 1 cycle. And again, here we have another look at that. So the time period that it takes for 1 cycle to complete is interesting to us in radio, because it has to do with what we refer to as wavelength. It's the distance of travel of a radio wave over the time period of 1 cycle. And radio waves are like light. They travel at just about the same speed. And we're in the metric system. Okay, it is 186,000 miles a second, but it's 300 million meters per second, and that's the number that we use. So 300 million meters per second is the speed of light and the speed of radio waves. So you know the speed, and we know the period, okay? And there's a relationship between frequency and period. And the period is calculated as 1 over the frequency, where the frequency is in hertz. And from all this, by knowing the speed, 300 million meters per second, and the time period, we can determine the wavelength of that particular signal. There's an easy formula coming up here, but this is more kind of background material here for you. More definitions. Wavelength is measured in meters. Remember, we're in the metric system. And it's the distance from an antenna measured between successive peaks on an AC wave. So here we have our antenna over here, and it's radiating. And if we take the same spot on the wave, okay, at the peak, and we measure over here, and this is how far it travels during this time period is called the wavelength of the signal. And the answer is always in meters. And the relationship between wavelength and frequency is that which determines how big we build antennas. The concept to consider is that frequency is where you tune your radio, and wavelength determines how big you build your antenna. So we have the ARRL color chart. It's in your book on page 1-23, but I'd be happy to send you one of these if you don't have one already. And you'll see that the various frequency ranges that amateurs can operate in the United States are indicated as meter bands. The 80 meter band, the 40 meter band, the 20 meter band, the 15 meter band, the 10 meter band. That has to do with wavelength. And there are frequencies also indicated in there, which is what we use in radio tuning primarily, when we're moving the big knob on the radio and trying to get it set up. So you can find these here at this URL if you'd like to download a PDF of these. But if you'd like a printed copy, it's not laminated. I say it all the time, but people think it's laminated. It is glossy. It's 8.5 by 11. This is the only size I have. If you'd like one of these, just send me an email to w4eey@arrl.net and say, Gary, I would like to get one of those color charts, and here's my mailing address. I can't do anything without a mailing address, please. So do that, and we'll get one out to you. And every ham has one of these, or should have one of these, in their ham shack next to their operating position, so you can make reference to it all the time. You may be old enough to remember back when we were talking about frequency, we didn't talk about what we say now, hertz. We talked about cycles per second. That was how it was referred to. So 1,000 cycles per second is the same as 1 kilocycles per second, or 1 kc. 1,000 kilocycles is the same as 1 million cycles per second. So there was a move. But back in the 1970s, the scientific community wanted to honor this gentleman, Heinrich Hertz, a German physicist. And so they said, we're going to rename the unit of frequency to the hertz. And so nowadays everything is in hertz, but it means the same thing as cycles per second. And if you like to go antiquing or flea markets and looking at stuff, you can tell if the radio has markings on it for kilocycles and megacycles, you know definitely it's pre-1970s. Whereas radios, even in the 1970s afterwards, had the new designation with megahertz and kilohertz. So the radio frequency spectrum, I use that word, is kind of like a rainbow. It has different bands, and we have names for them. Very low frequency is the lowest. Low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, and extremely high frequency. And then after that, we start to get into the visible and light spectrum over here. For our purposes, we are most interested in the high frequency area right here, which is from 3 to 30 megahertz. And then the very high frequency range from 30 to 300 megahertz, and ultra high frequency 300 to 3000 megahertz. If you buy your first HT, like this TID Radio H3, for example, this little radio is a VHF and UHF radio. It does 2 bands. So it'll do the range between, well, it won't do transmit on all of these frequencies, but in the 2 meter band is 140 megahertz. That's VHF. In the 70 centimeter band, we're talking wavelength there, it's about 444 megahertz, thereabouts. So this is a VHF and UHF radio, and that's what we're talking about here, VHF and UHF. If you think we've got a hard job, think about the FCC. They have to manage the radio spectrum, the broadcast spectrum, all cellular phones, everything. And so they have to go from the very lowest frequencies up to the microwave and beyond frequencies, and they have to allocate them and keep them separate and keep them compatible with other stuff. So that's frequency allocation that the FCC is involved in. Back even before Heinrich Hertz, well, not before him, but back in the 20s, a lot of radios actually didn't have frequency markings. They had wavelength markings only. So if you find a really old radio, you can look for that. And again, remember, we're talking about wavelength is the distance a radio wave will travel with one complete cycle. So I said there's a relationship, and it's relatively easy to work with. And it's this pyramid you see here. And on the top we have speed. This refers to the speed of light. Frequency over here. And wavelength over here. And what this triangle is telling you is that if you know the frequency, you can calculate the wavelength, or if you know the wavelength, you can calculate the frequency. And speed, we use 300, representing 300 million meters per second. So 300 is on the top. And down below here is frequency in megahertz. And when we do that, we get these formulas. Frequency in megahertz is equal to 300 divided by the wavelength in meters. So if we know the meter band, like the 20 meter band, well, we can calculate the approximate frequency by taking 300 divided by 20, and that'll give you a frequency range. Or if we were trying to find the wavelength, we can take 300 and divide it by the frequency in megahertz. Units are important here. And frequency and wavelength are inversely proportional. So the higher the frequency, the smaller the wavelength, which is why we say the VHF 2 meter band, well, 2 meters is a little bigger than 6 feet, but 70 centimeters is only about like that. So that's the difference in wavelength just on those 2 bands. So here's the pyramid with the numbers there. 300, representing 300 million meters per second. Frequency in megahertz over here, and wavelength in meters. We'll do some practice problems here in a second. But here's a general question. As frequency increases, what does wavelength do? Yeah, I'm seeing, yeah, it goes down. They're inversely proportional. And as wavelength increases, the frequency goes down as well. So yes, indeed, they're inversely proportional. All right, this is a little silly, but this is the proper way to write megahertz. It's capital M, capital H, small z. And the proper way to write kilohertz is small k, capital H, small z. All right, keep that in mind. Oh, look at this. So this is my symbol to tell me, Gary, it's now time to walk over to the smartboard and let's do some practice problems together and see how we do. The smartboard is new to us here in the studio, so let's see if we can make it work. Hi, here I am. Here's the smartboard. And let's get on to practice problems. We're going to do some metric conversion, and we're going to do frequency and wavelength problems. So our first practice problem is how many milliamps is 7 amps? So let's go to the board, and so a milliamp is 1/1000th of an amp. So 1 milliamp is equal to 0.001 amp. All right. Well, how many milliamp is 7 amps? Oh, and I got to tell you, I've been in electronics and ham radio for a number of years, and as an old timer, I have something that we call knowledge bias. I'll acknowledge it right now. I think, oh, everybody knows this. So I'm trying to slow down. I'm trying to be empathetic, because if it's new to you, you are not going to intuitively. I mean, I already know the answer, but it's not immediately obvious. So I'm going to try to work through the problem, and hopefully it'll come clear to you. I just wanted to mention that. All right. So 7 amps, if we were going to write it over here on this side, 7 amps, the decimal point is there. And then if we put 3 zeros, well, 7 amps, Gary, don't forget your units, is the same as 7,000 milliamps. See that? Amps is 1 amp is 1,000 milliamps. Are you able to take this full screen? Yeah, you were doing it. Okay, good. I couldn't see it there. Okay. Oh, that's right. This monitor just shows this camera. This monitor shows what's on the air. I gotta get used to this. Okay. Anyway, so okay, that's our first one. Let's see if we got it right. Yes, 7 amps is the same as 7,000 milliamps. All right, next one up. How many kilohertz is an RF signal of 3,500,000 hertz? Oh, kilohertz. So 1 kilohertz, remember it's small k, capital H, small z, is the same as 1,000 hertz. Probably not going to have enough room to put this up here, but so we're asking how many kilohertz. Well, the trick is that we move over 3 places. That 3,500,000, we get rid of that, and so 3,500 kilohertz is the equivalent. I think I just knowledge biased it. I'm sorry. But that's the answer there. 3,500 kilohertz is the same as 3,500,000 hertz. Let's see if I got it right. Yes, right there. Practice, and it'll come clear to you here. All right. How many volts are equal to 3 kilovolts, 3 kV? So 1 kV is 1,000 volts by definition. So 3 kV is going to be 3,000 volts. Yep, so it is 3,000 volts. So how many volts are equal to 5 microvolts? How many volts? Well, okay. I got to move over a little bit. 5 microvolts is the same as 0.000005. That's 5 millionths of a volt. Oh, and that's the answer. Or 5 times 10 to the minus 6th. Because 1 microvolt would be in this space there. So let's see. There it is. 511 millionths of a volt, or written out with decimals over here. So what is the equivalent of 1,000 millivolts? All right, that's 1 millivolt is equal to 0.001 volt. I got to improve my handwriting. Well, if we have 1,000 of these units, we'll put it there. And the decimal point is there. 1,000 millivolts is the same as 1 volt. Yep, so it is. An ammeter, measuring current, measures 5,000 milliamps. How many amps is this? All right, so again, 1 milliamp is equal to 0.001 amp. We have 5,000 of these guys. We move over 3, and the answer is 5 amps. 5 amps is the same as 5,000 milliamps. And a frequency readout shows 7.150 megahertz. What would this be in kilohertz? So the standard technique is we would move the decimal point over 3 places. So 7.150 megahertz is the same as 7,150 kilohertz. We're changing from units. I'm giving you a couple of different ways to do it here, and go to that YouTube video that I gave you the reference on, and I'll tell you some more techniques. There we are, 7,150 kilohertz. How many microfarads are 5 million picofarads? Oy vey. So 1 picofarad is equal to 0.00000000001 farad. And if we've got 5 million of these, so we put the 5 here, and there's the 5 million. And we're asking how many microfarads. Well, this is the microfarad. It's 6 places over, so the answer is 5. It's the same as 5 microfarads. All right, 21,500 kilohertz. What is that in megahertz? Well, megahertz is a bigger unit by a factor of 1,000, and we can get there by moving the decimal point over 3 places and make that a decimal point, and then it's 21.5 megahertz is the same. And a frequency readout says 5,125 megahertz. Well, what is this in gigahertz? Well, 1,000 megahertz, I'm giving you different ways to look at it here, is equal to 1 gigahertz. So if we've got 5,000, that's going to be the same as 5.125 gigahertz, if you can read my writing. Hey, hey. All right, enough of that. Let's look at some frequency and wavelength problems. Here's our triangle again. The speed of light on top, 300. Frequency in megahertz down here, and the wavelength in meters. So our first question is, the frequency is 14.2 megahertz. What is the actual wavelength? So we would go back to our pyramid here. Well, let's see if did I put the pyramid in the next one? Yeah, I did. All right, so the frequency is 14.2. So we know 14.2. And the trick on this, come back to the camera just for a second, is you put your thumb over, you put your hand over the thing you're trying to find. And it reminds you that it's 300 divided by 14.2. So 300 divided by 14.2 is, I didn't bring a calculator over here, so I'm going to cheat, 21.13 meters. Now I know that 14.2 megahertz is in what we call the 20 meter band. If you get one of the color charts and you look on the 20 meter band, you'll find that 14.2 is pretty much right in the middle. But it says 20 meters, but this says 21.13. This is right. This is an approximation. These band names are approximate, so keep that in mind. But if you're building an antenna, half-wave dipole antenna is the most common. We'll talk more about it in an upcoming class. It would be half this length, half of a wavelength. This is a full wavelength, and half of that then would give you the length of an antenna that you could build for this frequency. All right, the wavelength is 10 meters. What is the frequency? I don't know what I forgot what they have on the next slide. Okay, here we go. So it's 10 meters. So over here, it's 10. We're trying to find the frequency. And smartboard, stop that. So it's 300 divided by 10. I can do this one. 30. Well, the 10 meter band, if you look on the color chart again, 30 is the very top end of the 10 meter band. Again, remember, these are approximate. This is actual. Yep. Wavelength is 10 meters. What is the frequency? 30 megahertz. That's what we said. All right. You did it. At least you survived my attempt to get us there. So, all right, let's go back on over. Now we're going to actually answer some real test questions. Well, these were close to real test questions. All right, here we go. For section 2.1, test questions, and you can go ahead and unmute. We have what we call the 3-second rule, so we'd like you to, when we see the question, I'll read the question out, wait 3 seconds, and then tell me what you think the right answer is. And this is, again, more a measurement of me than it is of you. All right, so what is the relationship between, and we never spotlighted myself. Somebody should say that. Gary, you forgot to make yourself bigger. I apologize. I should have done that early on for the folks in the Zoom classroom. That should look a little bit better. Now you can read it. Sorry. So what is the relationship between wavelength and frequency? What do you think?
B.
It's B. Wavelength gets shorter as frequency increases. Good. And what is the formula for converting frequency to approximate wavelength in meters?
Charlie.
Not Charlie.
D.
Remember,
Delta.
It is delta, yeah. Remember, the 300 is up on top. So it's wavelength in meters equals 300 divided by the frequency in megahertz. Maybe it's a poorly worded question and answer, but that's what it is. So in addition to frequency, which of the following is used to identify amateur radio bands?
Wavelength and meters. A.
Alpha.
Alpha, yes indeed. And I mentioned they're approximate, they're not direct. Okay, so what frequency range is referred to as VHF?
Bravo.
Baker.
Bravo, indeed. 30 to 300 megahertz is VHF. The FM broadcast band is in the VHF range. And what frequency range is referred to as UHF?
Delta.
Everybody see that?
Yeah, no,
It's,
delta, yeah.
it's the next
megahertz.
band up, delta. And I want to point something out here. So here we say, 300 to 3,000. Look up above, 300 to 3,000. Oh, but look, that's kilohertz. And we're dealing in megahertz. So make sure you don't get tripped up by the unit. So what frequency range is referred to as HF, or high frequency?
Charlie.
Charlie. 3 to 30 megahertz, yes indeed. And what is the approximate velocity of a radio wave in free space?
Bravo.
Bravo.
Yep, 300 million meters per second. And what is the unit of frequency?
Alpha.
Heinrich Hertz.
Alpha.
Yes, indeed. And what describes the number of times per second that an alternating current makes a complete cycle?
Delta.
Delta.
It's the number of times per second, that's the frequency, delta. And how many milliamps is 1.5 amps?
Charlie.
It is the same as 1,500 milliamps. And which is equal to 1,500,000 hertz?
Alpha.
I've heard alpha, yes indeed, it is 1,500 kilohertz. And which is equal to 1 kilovolt?
Charlie.
C.
Yeah, a kilovolt is 1,000 volts, so 1,000 volts. And which is equal to 1 microvolt?
Delta.
Alpha.
It is alpha, 1/1,000,000th of a volt. That's a microvolt.
No, micro.
Micro. The millivolt would be a 1/1000th, but micro is 1/1,000,000th. And which is equal to 500 milliwatts. What is the equivalent?
Baker.
What? Charlie.
No, Baker is what we heard first, and that is the correct answer. It's the same as half a watt, or 0.5 watts, is 500 milliwatts. 1,000 milliwatts would be 1 watt, so 500 milliwatts is going to be half a watt. And which is equal to 3,000 milliamps?
Delta.
Delta.
Yeah, it is the same as
Delta.
3 amps. And which is equal to 3.525 megahertz?
Charlie.
3,525 kilohertz is the same. And which is equal to 1 million picofarads?
Baker.
Yeah, it is the same as 1 microfarad. And which is equal to 2,840 kilohertz?
Delta.
Not delta. Oh, wait a minute.
Alpha.
Yes, delta. I looked at the wrong one. It is delta. I was looking up at the alpha, but it's the wrong unit. I don't have my glasses on. 28.4 megahertz. Ooh, the instructor got caught. So which is equal to 2,425 megahertz?
Charlie.
Charlie.
Yes, and
Charlie.
2.425 gigahertz is the same. We're just doing unit conversions here. And what does the abbreviation RF mean?
Alpha.
Alpha.
Radio
Alpha,
frequency
alpha.
signals of all types. And what is the proper abbreviation for megahertz?
Delta.
Delta.
Capital M,
Delta.
capital H, small z. And what is the proper abbreviation for kilohertz?
Delta.
Delta.
Small k, capital H, small z. Yay! That's one of the harder sections in the book, so I'm very proud of you. You did good. If it's still a little confusing, don't worry about it. Go back and review and reread it. It'll come clear to you, I'm pretty sure. All right, section 2.2 is a little shorter, radio equipment basics. And this is, that was my old, by the way, my old station at my old house. We'll look at some more pictures here in a second. But the basic ham radio station, this is what it consists of. I'm going to go ahead and mute everybody because it gets a little noisy in the background there. Okay. You have a transmitter. You have a receiver. You have a switch, a transmit-receive switch. And you have a feed line that goes out to an antenna. And so back in the day, we had separate receivers and transmitters. These are the Kenwood twins. I lusted over these radios, but I couldn't afford them. My paper route just wasn't lucrative enough to go for these. But separate receiver, separate transmitter, and I think in one or the other there was a TR switch built in. Well, nowadays we don't use separates. You can still find them at Hamfests, but no longer manufactured. What we do now is use transceivers. And a transceiver has both functions indicated into one unit. So here's our transceiver. It's got various devices where you can add information to the radio frequency carrier by modulating it, either via a Morse code key or a microphone. You can listen to what's going on through a speaker over here or headphones. Most amateur radio transceivers are what we call 12-volt radios. They were originally designed for mobile use or could be used in a car, and so you need to get a power supply to provide 12 volts. Actually, it's 13.8 volts is the standard from your normal 60 cycle 120 volt AC house current. So you have a DC power supply that is powering thing. And this transceiver might be 100 watts out, but if you want to go to the full legal limit, 1,500 watts, then you need something called a power amplifier, also known as a linear amplifier, that'll take it up to that power level and send it out to your antenna. So this is a typical block diagram of a current station. And this radio was discontinued this last year, but it's a pretty one. It's the ICOM IC7851. When it was new, it would cost you about $13,000. You don't need to get that one. But ICOM makes great radios, and they've just come out with their new IC7300 Mark II radio, which I would highly recommend you take a look at if you're thinking about an HF radio. It's not really released to the market yet. They announced it, but it looks like it's going to be a good one. The original 7300, they sold over 100,000 of them, which is it's the best-selling radio ever. It's a record. So again, here's my old ham shack back over in Greenville County, and had a flex radio sitting over there. I had the Maestro controller down here. Here I am contesting, I think. Well, then moved and came over to Anderson County, and so this was my station before. It's since changed, but again, we have the Maestro. And you don't see the radio here. I'll show you where it is. And then I have a second radio over here for VHF, UHF. It's a Yaesu FT991A, some power monitoring, some antenna control units over here, logging software, etc. over here. This is a closer look at my HF station, and again with the Maestro, and then the VHF station over here. Now, because of my situation, power amplifiers generally require 240 volts to work at full power. And I didn't have 240 volts available in my office there, but I did have it available in a storeroom just off of my garage. So I moved my flex radio there, the actual radio unit, and my power amplifier. Out to a little room there, and in that room I have 240 volts available to power the amplifier, and then going out through a hole in the wall is my antenna cables. And I don't do good with heights anymore. I used to be able to climb, but I can't do that much anymore. So my antennas are actually on top of my garden shed. I have a hex beam antenna, a rotatable HF antenna, and then a bunch of VHF and UHF antennas there. I have a bunch of wire antennas. You can barely see one there. Bruce helped me put up a full 80-meter horizontal loop, which is a great performer. And it's actually not visible in this picture. But then I got the bug. I wanted a new radio, and ICOM came out with a new radio. It doesn't replace the 7851. It's not in that same caliber, but it's their current top of the line. It's this, the ICOM IC7760. And notice it's a two-part radio. It's got a control unit over here, and it's got the main radio section over here. It dropped in place of my flex. And so the flex is now downstairs in my workshop, and we're using the Maestro here in the studio. And so let me just briefly go back over here and just show you a little bit about the flex and the Maestro. This might take a few seconds because I have to change inputs. And when we did it earlier, okay, seems to be working. All right. So here we are. This is the 40-meter band. This is live. This is what's going on right now. And the Maestro unit is over here in the corner. It's got what I call the big knob, which is what you do the tuning with. But I wanted to show you, if we just push on the screen here, you'll see here in the center the various amateur radio bands. 80-meter band, 40-meter band, 20-meter band, they all correspond to the color chart. So this is how you change bands. We're on the 40-meter band right now, which is a 7 megahertz frequency. I'll turn the audio up, but I have no idea what's going on.
This is about 200 miles north. But anyway, we're back here. I'll go ahead. All right, Eureka, Topeka, huh? Conrad, hold on a second. Norm, you got Conrad. He's in Kansas. Kilo 0, Foxtrot, Charlie Lima. Oh, roger that.
So we won't hang on there, but we'll be using the radio to demonstrate various modulation modes. We'll be listening to signals coming from Morse code stations, maybe radio teletype, single sideband, which is what I like to do. So more to come. But you don't need anything as fancy as this. Because as I mentioned before, the TID Radio H3 is a ham station. Inside this is a receiver, a transmitter, a transmit-receive switch, and an antenna. Everything we saw on the block diagram, if you go back to the laptop just for a second, Bruce, this too, your handheld transceiver, is a ham radio station because all of those things are built into it. And the nice thing about the little radios is you don't have to just rely on their output power, which is typically about 5 watts, because we can use local radio repeater systems. Repeaters receive a signal from one of these small radios on one frequency and transmit it back out again on an adjacent frequency, very near to it, at higher power levels and from great height. And so that's why with one of these little radios and a good repeater system, you can go 60 to 70 miles through a repeater. And repeaters are very much like what we saw before. They have a transmitter, they have a receiver, but in place of the TR switch, they have a special filtering system here called a duplexer that allows both the receiver and the transmitter to be connected to the antenna at exactly the same time without interfering with each other. And at high power levels, 100 watts out or something like that, that can be no mean feat. So a radio repeater looks like this. This is the electronics part of the radio repeater here, but this is the filters. The filter systems are bigger than the others, and that's what allows the receiver and the transmitter of a repeater to be connected to an antenna at the same time. Oh, we're ready for questions. So what is a transceiver?
Alpha.
You hear that? You see that?
Alpha.
Yeah, it's a device that combines a receiver and a transmitter. And that, ladies and gentlemen, is the end of chapter 2. You made it, and we made it in an hour. Any comments or questions before we go home tonight? And let me turn off my spotlight so we can see you better.
I have a question.
Yes, please.
That VHF, UHF, SHF, the chart in the book,
Yes.
it says that that's arranged by characteristics that are similar. What characteristics are similar that they've gotten them divided up in these?
Okay. That's an excellent question, and that's the first time anybody's ever asked me that question. And I think what the right answer to that is that the high frequency band, 3 to 30 megahertz, uses as a primary mode of communication ionospheric propagation. What does that mean, Gary? What it means is from your antenna, signals go up to the ionosphere. We'll talk more about this as we go along, and it's refracted and comes back down thousands of miles away. And so signals between 3 and 30 megahertz are all subject to ionospheric propagation and having signals go a long distance. From 30 to 300 megahertz, it's primarily line of sight. There isn't any, it goes up to the ionosphere but goes straight out into space. And is not refracted back down to the ground. So that's a characteristic that's common to that. UHF is even smaller wavelength, and it has better penetration through buildings than VHF does. What other characteristic is? It's very similar to VHF, but that would be my best answer off the top of my head.
Thank you.
Thank you, Donna. Anything else?
Thank you, guys.
All right, so I want you to please read chapter 3. It's another one. This time we're going to get you into electronics and circuits and things. Oh my. So don't let your head explode, but you take your time going through the chapter, and we'll try to make it clear next week. Until then, let me say 73. See you next week.
73.
Yep.